Hello students, good evening all of you. In this video, let us discuss Williamson ether synthesis, okay, and some problems based on Williamson ether synthesis, okay. So actually here, what is this Williamson ether synthesis? It is a chemical reaction used for the preparation of the ethers. That means here, alkyl ethers can be prepared by Williamson synthesis, okay. So here it is actually substitution reaction. Okay. So this one proceed through the bimolecular nucleophile substitution reaction, simply known as a SN2 reaction. Okay. So in SN2 reaction, so you know that primer alkyl halides are more reactive. Okay. And the strong nucleophile favors SN2 reaction. Okay. So conditions for the SN2 type reaction, the strong nucleophiles favors SN2 reaction, and primary alkali halides are more reactive than the secondary alkali halides in SN2 reaction. So here primary alkali halides means simple alkali halides are most suitable for SN2 reaction, and the charged nucleophiles are most suitable for the SN2 reaction, because SN2 reaction is a single step reaction. So that in those reactions, nucleophiles start the making a bond from the back side of the leaving group. Okay. So here, so actually here nucleophiles are the two types, neutral nucleophiles and the charged nucleophiles. Charged nucleophiles are more reactive than the neutral nucleophiles. Okay. So this Williamson ether synthesis involves a reaction between the alkoxide and alkyl halide. Okay. Your sodium alkoxide or potassium alkoxide on reaction with alkyl halide will get the ether through the SN2 mechanism. Okay. Through the SN2 mechanism. So here in this case, some conditions need to be discussed. Okay. So first of all, let us discuss the reaction. So alcohol on reaction with sodium or sodium hydride. Okay. So we'll get the sodium alkoxide. Okay. That release the H2 gas, because here this is the acidic proton. Sodium is an alkali. Here sodium hydride has a basic nature Na plus H minus. So H minus remove the here H plus, will get the H2 gas. So now here, as a result of this acid-base type of reaction, we will get the charged nucleophile Ro minus Na plus. Now here, after the acid-base reaction, adding alkali halide, so here that involves SN2 type reaction. So here Ro minus attacks on the alkali halide and leaving out the X minus. So through the SN2 reaction, we will get the ether. Okay. So here that leaving group, X means here simply chlorine, bromine or iodine or any better leaving group. Okay. Sulfonates are the better leaving groups. You know this one. So here, why these sulfonates are better leaving groups? Because this is the conjugate base of the stronger acids, sulfonic acids. Okay. Sulfonic acids are stronger acids. So conjugate base is a very weak base. So weak base are the good leaving groups. Okay. So here we can use this sulfonate also. So here Ro minus, here Na plus, here Ro minus attacks on this one, leaving out this. So here we'll get the alkyl ether similarly. Okay, that's it. So here in this case, the main condition is it is a SN2 type reaction. Okay, we have taken charged nucleophile, but here which type of alkyl halides most suitable for this Williamson ether synthesis? Okay, that means for this SN2 type reaction. So here that alkyl halide must be very simple alkyl halide. Okay, that must be simple alkyl halide. That is methyl halide or primary alkyl halide or allyl alkyl halide and benzyl alkyl halide. That must be very simple alkyl halide. Okay, so let us take methyl chloride and ethyl chloride, N-propyl chloride and N-butyl chloride, and we can take the allyl chloride, we can take the benzyl chloride. Okay, the alkali halide must be simple. Okay, so because in this case in SN2 reaction, primary alkali halides are most reactive and simple alkali halides are most reactive. Okay, in case of the second alkali halide, tertiary alkali halides, so there is a steric hindrance is working. Okay, so because of the steric hindrance, second alkali halides, tertiary alkali halides are not involved. Of course, a secondary alkali halide can be involved in SN2 type reaction based on the conditions, but tertiary alkali halides here the most not suitable for the SN2 type reaction. Okay. So here this is the roughly Williamson ether synthesis. Okay. So here let us discuss some problems based on this Williamson ether synthesis. Okay. The main key point is that alkyl halide must be simple because it is SN2 reaction. In SN2 reaction, primary alkyl halides and simple alkyl halides are more reactive. Okay. And nucleophile must be charged nucleophile. So here as a result of the first acid base reaction, we'll get the sodium alkoxide that is acting as a strong nucleophile, favors the SN2 reactions. Okay. For SN2 reaction, this alkyl halide must be very simple. Okay. So let us discuss some problems. Okay. Yeah. So how to prepare the following ethers from Williamson ether synthesis? Okay. So it is a dimethyl ether. Okay. It is a dimethyl ether. This dimethyl ether can be prepared by taking methyl alcohol. So on reaction with sodium hydride, so that produces CH3, O minus, Na plus, and then reaction with methyl chloride. Okay, because both are the methyl groups. So here in this case, nucleophilic substitution, so that gives a dimethyl ether. It's a simple alkyl ether because the same alkyl groups are the present and both alkyl groups are very simple. Okay, so there is no problem for the preparation of the dimethyl ether. But here in this case, it is a tertiary butyl methyl ether. How to prepare this ether from the Williamson ether synthesis? Okay, in a Williamson ether synthesis, that reaction proceed through the SN2 mechanism. Okay, in SN2 mechanism, simple alkyl halides are the more reactive. Okay, so here in this case there are the two possibilities. Okay, so here that path 1. Okay, that path 1 taking this one CH3 Cl and here Na plus O minus CH3 and CH3. By taking this combination, okay, by taking this combination we can prepare this ether. Okay, and next here another possibility, your path 2 CH3ONA and this chloride CH3 and CH3 this CH3. Okay, so there are two possibilities for the preparation of this ether. Okay, but here between these two possibilities, here one possibility is the best possibility. Okay, so in this case simple alkyl halide methyl chloride, here in this case here tertiary alkyl halide. Okay, so by taking tertiary alkyl halide sodium methoxide, here we will get the different product as a measure because this tertiary alkyl halide is less reactive in SN2 reaction. Okay, this tertiary alkyl halide is not suitable for the SN2 type reaction. But in this case, the simple alkyl halide, this is the strong base as well as a strong nucleophile. So here in this case, this one easily possible. So that means this is a suitable method for the preparation of the tertiary butyl and methyl ether. But here in this case, this tertiary alkyl halide, this is a strong base as well as strong nucleophile because this is the conjugate base of which one? Methyl alcohol. This methyl alcohol on reaction with sodium hydride will get the sodium methoxide. This methyl alcohol is a weaker acid, so conjugate base is a very strong base. And as well as charged species, that is a strong nucleophile that favors SN2 reaction as a strong nucleophile, and as a strong base that favors the E2 reaction. In E2 reaction, okay, in E2 reaction, tertiary alkyl halides are more reactive than the secondary alkyl halide. Okay, but in SN2 reaction, primary alkyl halides are more reactive. Primary alkyl halides are more reactive. Okay, tertiary alkyl halides are least reactive. So here in this case, this tertiary alkyl halide is not suitable for the SN2 reaction. But here in this case, it is the most suitable for the E2 reaction because this is a strong base. Strong base favors an E2 reaction. Okay, of course, strong nucleophile. That strong nucleophile favors SN2 reaction, and strong base favors the E2 reaction. This is both strong nucleophile as well as strong base. But here, the alkyl halide is a tertiary alkyl halide. It is suitable for the E2 reaction, but not SN2 reaction. So here in this case, we will get the elimination product CH3O minus that remove the H plus from this carbon. Okay, H plus from this carbon and remove of the Cl minus. So here CH2 double bond here, CH3 and CH3. Isobutene is a major product. Isobutene is a major product. And here the tertiary butyl methyl ether is a minor product. Okay, almost 2%, that is the minor product. Here in this case, majorly 90% elimination takes place because the tertiary halide is not suitable for the SN2 type substitution. Okay. Now here coming to this one. Similarly here in this case, so from this example we can finalize that alkyl halide must be simple, and here that base must be bulky base. Okay, larger size base or larger size nucleophile. Okay, so here in this case again here the sodium tertiary butoxide, here in this case here halide. So here the suitable combination is CH3 CH2Cl plus O minus here Na plus CH3 and CH3 this CH3. This combination is a suitable combination for the preparation of this one. Okay. So because it is a primary halide, of course it is a strong base. Here elimination product is very less. Okay. So this method is this combination is suitable for the preparation of this tertiary butyl ethyl ether. Okay. That's it. But of course here by this combination we'll get the CH2 double bond CH2 also, but it is a minor product. Okay, because your base, your secondary halide that can remove the proton from this carbon, but this alkene is a minor product. Here majorly substitution takes place because the primary alkyl halides are less reactive in a E2 reaction. Okay, now here coming to this one. Again here in this case, the taking a butoxide, that is a tertiary butoxide, sodium tertiary butoxide, and this is the halide. That means here the combination is pH CH2 halogen plus O minus NaCCH3 thrice. Okay, it is suitable combination. Of course, if you take like this here, pH CH2O Na and halogen, this tertiary halide is not suitable for the SN2 reaction. So here in this case, that means elimination mostly favorable. Okay, it is a base as well as nucleophile, but it is a tertiary. This tertiary is not suitable for the SN2 reaction. But here in this case, it is a simple alkyl halide benzyl halide is suitable for the SN2 type reaction. So here this is a suitable combination for the preparation of the benzyl tertiary butyl ether. Okay. So here in this case, that for the preparation of the Williamson ether synthesis, that alkyl halide must be simple alkyl halide. Okay, that's it. Yeah. So let us discuss some more examples here. Okay. So how to prepare this ethers by using Williamson ether synthesis. Okay. So in this case, there are the two chances. Either cut this one or cut this one. Okay. So here chance one is a PHONA and halogen CH3. Okay. And other one PH, that means here we can take the chlorobenzene. Okay. Let us take chlorobenzene and NaOCH3. Okay, this combination is a suitable combination because in this case, here this is the nucleophile. This is not involved in a nucleophile substitution reaction. Aryl halides are not involved in a nucleophile substitution reaction. Either SN1 or E1. Aryl halides are not suitable. Okay, so here this combination is not chosen for the preparation of this anisole. For the preparation of this anisole, a sodium phenoxide and methyl halide is most suitable. Okay, that's it. Because aryl halides are not involved in a nucleophile substitution reaction. Here, this one also same. Those vinyl halides are not involved in a substitution reaction. Okay, so because of the resonance stabilization. So again here, the corresponding sodium alkoxide and this is the halogen. So here CH2 double bond CHO minus plus the corresponding halide CH3. Okay, and next here coming to this one, again here there are the two possibilities. Okay, so here either this bridged halide and sodium methoxide, and another possibility sodium alkoxide and methyl halide. This combination not suitable because it is a bridged halide. Bridged halides are not involved in substitution reaction. Of course, it is a tertiary one, so SN2 type reaction not suitable. Okay, and next here, this one is a simply halide. So here, this is acting as a nucleophile. Substitution takes place. So it is a suitable method for the preparation of the this ether. Okay, that's it. So now here, this ether cannot be prepared by the Williamson ether synthesis. Diphenyl ether cannot be prepared. Why? Because we should take one of the halide, one of the aryl halide, and the other one is a sodium phenoxide. Okay, sodium phenoxide. Yeah, this aryl halide is not involved in a substitution reaction. The aryl halide is not involved in a substitution reaction. But here, the one interesting point is we can prepare this ether. So oxygen here, this is the phenyl, this is the NO2 group, and this is the NO2 group. This ether can be prepared. Okay, even one NO2 group is present, that ether can be prepared by the Williamson ether synthesis. How it is possible? Okay, so you know that AR-SN2 reaction, addition elimination mechanism. Okay, addition elimination mechanism are aromatic biomolecular substitution reactions. Okay, so that might be studied in aryl halides. Aryl halides are generally not involved in substitution reaction, but aryl halides having electron withdrawing group can be involved in a substitution reactions. Okay, so taking this base, sodium phenoxide. Okay, so here this combination is suitable. Aryl halides having electron withdrawing group are involved in a biomolecular aromatic substitution. That means here ARSN2, those reactions are also called as a addition elimination reactions. Okay, so here substitution takes place. That's it. Okay, here X minus leaving by the addition elimination mechanism. It is a two-step process. Okay, in one video I will discuss about the aromatic biomolecular nucleophile substitution reactions. Okay, so mostly in next video I will discuss about that one. Okay, so this one can be prepared by the Williamson ether synthesis, but diphenyl ether cannot be prepared, and ditertiary butyl ether cannot be prepared because here for the taking of this ditertiary butyl ether, we should take tertiary butyl halide. Okay, it is a bulky base and bulky nucleophile. It is a tertiary halide. It is not involved in a substitution reaction, SN2 type reaction. So here elimination mostly favorable. Okay, it is not suitable substrate for the SN2 type reaction. So here in this case, elimination is favorable. So isobutene is the product. Okay, this base remove the proton and leaving out the X minus. Okay, so isobutene is a major product in this reaction. So we cannot prepare successfully this either. Okay, ditertiary butyl either we cannot prepare. And here, of course, we cannot prepare this either also by the Williamson ether synthesis because we should take phenoxide ion. So here in this case O minus Na plus and tertiary halide. We should take tertiary halide. The tertiary halide is not suitable for the SN2 type reaction. Again in this case elimination is favorable. This one remove the proton and leaving out the X minus, again we'll get the isobutene as a major product. Okay, so that is about the mostly Williamson ether synthesis. So write down.